First things first, we got to predict them. Jill, what are our products going to be?
AL3 plus AL2.
You said AL2, S3. So talk to me, Jill. How did you get those products? Kind of walk me through your steps that you did. Brackets? What do you mean by brackets? Switch it. So we're switching partners, right? Guys, again, I tried to get you to do that all along. Switch it up. Are these the brackets you're talking about? Yeah, right? Outsides go together, insides. Now, how did you get your subscripts? I didn't see AL had a 2 over here, S have a 3, and I saw K had a 2. How did you get your new subscripts as products? What did you look at? What about the periodic table did you look at? The charge of the element. That's what's going to dictate it, guys. So for KNO3, K had a +1. NO3 is a polyatomic that had a -1. You have to do the crisscross method. Are you kidding me? There we go. There we go. All right. So you've got to do the crisscross method for your products. You cannot assume that they're going to have the same subscripts every time. Aluminum was a +3. Sulfur is a 2-. So we're going to take those, we crisscross those over. So that's what our new products should look like. But we're going to rewrite it as our balanced equation. On your quiz on Thursday, or Wednesday, I should say, excuse me, guys, you're going to have 3 lines. You're going to have the balance line, you're going to have the CIE. What do I call the CIE? What does that stand for? The complete ionic equation. More about that in just a second. Then you're going to have the net ionic equation. And we'll talk more about that in a minute as well. So for the balance, it's got to have what pieces to make it the full balanced equation? What are all the pieces I'm going to be looking for? States of matter. What else? Will there be charges with the balanced one? No, but what did you say? Coefficients. Those are the 2 pieces, guys, I'm going to look for. So yeah, we can rewrite K2S plus AL NO3 3 yields K NO3 plus Al2S3. So first things first, balance your equation. How will we balance this equation, guys? What should be our coefficients reading from left to right? 3, 2. Not 3, 2. 6, 1 is what you should have. Okay, that's what your coefficients should be. Is 3, 2, 6, 1. Now, how do I identify, or what tool will I use to figure out my states of matter? The solubility rules. And it's right here. Now, when we use our solubility rules, guys, as a review, what piece of my compound am I going to be looking for first on my solubility rules? One of 2 pieces. The what? The anion, right? The anion comes where in the compound? Last, okay? Now, why is that? Because, guys, if you take a look here on this table, most of them are anions. That's why we're going to look for the anion first. The cation would be one of the exceptions to the rule. So here, we're going to find out when you go through and do this, this is aqueous, this is aqueous, this is aqueous. Is aluminum sulfide aqueous? No, it's not. It's going to be solid, right? So, how do I know if it's aqueous or solid or what? If it's soluble, it means what? It can be dissolved, and therefore you have an aqueous solution. If it's insoluble, our state of matter is solid. Okay? So that's where I got those pieces. So, there's my complete balanced equation. Now I'm going to break it down into my complete ionic. So what should I see? This is something, guys, why I'm trying to drive it home is because every single year I see students not even think about what ionic means. Charges. You have to have the charges. So we're going to break them up. I'm going to use a different color just for the sake of visualizing. So if we go through, break up your compounds, draw those lines in. Okay? So this is going to be here and here. How many potassium ions do I have? 6, right? Because 3, guys, gets distributed not only to one element, but to both elements in your compound. 3 times 2 is 6, so I've got 6. K, what's the charge on that? Plus. All right. Do I have to put the 1 there? No, I don't. And we're just adding everything together. So then I have 3 sulfur ions. They have a 2- charge. All right, so there we go. I broke up my first compound. I still have the same amount of ions that I had up top. I just am now showing them as individual ions, not as a solute that's in a solution. Okay? So, then I'm going to add my next one. Do the same thing. Distribute this out to both pieces. All right, I can show. We're going to move away today from drawing arrows in, but again, I just want to show you where I'm getting the different pieces. So we've got 2 aluminum ions, 3+ charge. They have an aqueous state of matter because they are dissolved. How many nitrate ions do I have? 6. 2 times 3 is 6. NO3. The 1 minus charge. There we go. Breaking it up. So over here, I've got 6 K plus ions plus 6 nitrate ions. Again, parentheses around those polyatomics. And then I have, how many ions do I have here? How many aluminum ions do I have over here? Do I? Do I have any ions there with the last one? No, why not? It's a solid, guys. The only substances that you can break up are what? Aqueous. If it's something else for the state of matter, this is why it's so crucial that you have states of matter. If it's something other than aqueous, guys, you have to keep together. Whether it's liquid, gas, or solid, they've got to stay together. So here we've got Al2S3, and it's a solid. Now comes the net part. Net is what's left over after all your stuff is taken out in terms of like taxes and things like that. So, how do I go through and sift through all this information that's in my complete ionic equation? What am I looking for? It's got to be what, Tony?
Things that are exactly like.
Exactly like. So that means everything for the number of ions, the charge on the ion, and the state of matter. So take it piece by piece. 6K plus. You guys will go on a break in just a second. 6K plus aqueous. Do I see that over here on the right side of my arrow? Yes, so that's the same. I'm crossing those out. Do I see 3S2 minus aqueous on the right? No. So I'm going to keep that. Do I see 2 Al3 plus aqueous on the right? No. Do I see 6 NO3 minus aqueous? Yes, I do. So everything else, guys, I'm dropping down. That's my net ionic. I'm just going to keep in the same order. 3 S2 minus aqueous plus 2 Al3 plus aqueous yields Al2S3. So the only species, guys, that actually reacted were the sulfur and the aluminum. They came together to form a, what's a solid called that forms? A precipitate. Okay? Go ahead and take a break. We'll come back and do some more. All right, so when you go through, guys, and you analyze the solubilities of each compound in this example, this is what you should get for your balanced chemical equation. Okay? Again, the balanced part and the predicted products were taken care of for you. Now, do I anticipate you guys having to predict products on your Regents exam? No. I think they would give it to you. You would have to then make sure it's balanced and go from your states of matter. But as soon as I say that, what could probably happen? They want you to predict products. So we're going to continue to practice that the rest of the year. Okay? So, know how to use your solubility rules. If you realize, or if you see, guys, that you're still struggling with figuring out the correct states of matter for your compounds, you need to raise your hand, call me over so I can help you one-on-one when you're doing some practice, okay? Because it's something you've got to be able to look at. Now we're going to split them up. What states or what substances can I split up? They have to be what state of matter? Aqueous. Aqueous only. Anything else you have to leave together. So, I'm going to go through and do that very quickly. Keep your states of matter. This is where if you start to skip steps and you are like, man, I don't want to do all this writing, I don't want to put all the states of matter in there, you're going to lose it. Okay? Because then that's your piece, your guide that you're looking for to see which are my spectator ions or not. Nothing else is going to help you with that. All right? You have to know the states of matter. All right, so that's what I'm going to go through and finish here really quickly. Where you have polyatomics, I encourage you to keep parentheses around them. It just makes things a whole lot neater. Giving yourself ample space is important as well, so you don't run into, mushing everything together. All right, there's what the complete should look like. We've broken up every species that we can into their individual ionic components. Now we're looking for which ones stay the same. They're going to have the same charge and the same state of matter. Does barium change? Bueller? Does barium change? Yeah. Barium changes, so we're going to keep it. Does nitrate change? Anytime, guys, you see nitrate, you know that's going to be a spectator because are there any exceptions to nitrates? No. Every single nitrate is going to be soluble. Anytime you see a group 1 element, guys, they too are always soluble. So those will be canceled out. It's the other components that you're going to be looking for. So here goes our net. It's going to be barium ion plus sulfate with their charges yields barium sulfate. Just like that. Questions? Getting easier? It's a long process, right? I give you that. But if you follow the steps, guys, and you are neat and organized, this is not that bad, is it? Okay, it's not too bad. It's just long. All right, but it gives us understanding as to what's going on at the chemical level, those particles going on. Okay, so 2 hydrogen ions aqueous plus SO4 2 minus aqueous plus. Now this wasn't balanced. I didn't go through and do that. There needs to be a 2 here and a 2 right there. So you have 2 sodium ions plus 2 chlorine ions. All right, then we have 2 hydrogen ions plus 2 chloride ions plus 2 sodium ions. What do you guys notice? Why do you think this was the example that I wanted you guys to see? Everything here is going to cancel out, right? What do you think in real time we would actually see if we were to do this reaction out? These both, sulfuric acid and sodium chloride in solution, they're both clear solutions. What would you think we would actually see when we mix those together? Nothing. It would look exactly the same. Why? Because there's no reaction, guys. They are all soluble. They stay together. I'm sorry, they just stay as they are as ions. Nothing goes together. Where all the other ones we looked at, what would we actually see once we mix them together? A clump, something coming together, right? There could be some gases given off, temperature change, color change, all those types, all those different things, bubbles, right? Those things that we talk about, the signs of a chemical reaction that we've talked about this year. We would see one of those things or multiple things happen because you have a precipitate forming. That's solid, okay? Here, though, there's no net ionic. The reaction itself, there's no new reaction that's going to happen. They would just all be, instead of being, isolated as only 2 ions in a jar, now you have 4 ions in a test tube or in a beaker. Okay? So what we do in this case, all we have to say is that there's going to be no net reaction. That's it. Now, do you think you're going to see a lot of these examples on like a quiz or a test? No. So if you go through your solubility rules and you identify that everything is aqueous, what do you want to make sure you do? Double check and even triple check, guys. It can happen. If you go through and think, oh, everything's aqueous, all right, no net reaction, just go back and double check, because I have seen so many times my students, when they don't read things properly, they're going very quickly, all right, they will think, hey, no net reaction, but really there was something. So you want to just take your time and make sure that you have assigned solubility correctly. All right? Questions with that? All right, we're going to shift gears now, and we're going to talk about solubility tables. Have your reference packets out for this, and we're going to be on the next page or so in your note. Solubility curves, guys, they show us that, and they prove that, hey, as temperature increases, what happens? You can fit more stuff in your solvent. Okay? Why might that be? This is review from our last unit, or not even just last unit, but the last couple units. Why do you think as temperature increases, solubility is going to go up? You can get more solute in the same amount of solvent. What's that? What about things moving faster? What's that going to change?
The volume.
The volume, right? Volume is going to increase, guys, as temperature goes up. What law states that? well, gas law anyway. Liquids are similar. Okay, it's Charles' law. V1 over T1 equals V2 over T2. So as temperature goes up, our volume is going to. Particles are moving faster. They're going to spread out more. That's why we see that now. The ones like HCl. All right, let me use my highlighter here. HCl right along here. We've got ammonia gas going down here. And SO2, okay, they are exceptions to the rule. And then we can see, hey, some things like NaCl, it doesn't have a high solubility anywhere, no matter what temperature it is. It doesn't increase much. Okay, so there's different things that we're going to look at. So this shows the dependence of solubility on temperature. All right, how do we determine solubility of a given substance? So a couple of different types of questions you're going to be asked to do, and things that you want to be able to make sure you are aware of. Okay, so find out the mass of the solute needed to make a saturated solution. That term saturated, guys, that's a vocab term. What does saturated mean? Right, so it can't dissolve any more solute, so it means that it is full. Okay, a saturated solution, guys, is full. It's to capacity. All right, and then you can repeat for each temperature from that, and it shows you all those, and they're connected on that dot. So here's an example. Let's just dive right in. This, again, is not in your notes. We're just going to kind of talk about it together, and then you guys will do some practice problems. What substance has a solubility of 90 grams per 100 centimeters or milliliters of water at a temperature of 25? So how do we solve this problem? Okay, so table G is where you're going to be looking for. If it's asking you guys about solubility or how many grams can be dissolved, you've got to go to table G. They're not going to give that to you on your test. They're not going to give you a picture of it. You have to know that it's in your reference table. Okay, so how do we solve for it? It gives us 2 points. What are those 2 points?
25 degrees Celsius.
We have 25 degrees Celsius and we have 90 grams of solute. So we're going to match those 2 points up. Here's 90, here's 25, kind of in between. We're going to go over right about there. What substance then is that? You got to follow it up. Sodium nitrate. Okay? That's how we go through and we solve a question. That's kind of the first type that we'll see. Okay? Where you're given a temperature and a amount of grams of solubility, match them up. All right. What substance has a solubility of 200 grams per 100 centimeters of water? This one, guys, you wouldn't have a problem like this because yours go up to 200. Now, we could potentially extrapolate and think which one it might be, but we're not going to worry about that. So this problem, ignore. Now, we could also be looking for the temperature or the solubility, where you just have one piece and you've got it, and you're given a substance, all right, and then you've got to figure it out. So it's doing the same thing. So this is saying, what is the solubility of potassium nitrate at 80 degrees Celsius? Potassium nitrate. It's this line right along here that we're looking for. 80 degrees Celsius. We're going to go up to it. Oh, it doesn't go up there. You might have to extrapolate. Let's change this from 80, and let's say, let's make it 60. Okay? What would be our value? Right about there. About 105 to maybe 108. Okay? There's going to be some wiggle room because it is interpretation that's taking place. So you could be given a temperature condition, guys. You could be given a solubility, and you could have to be asked for the temperature, either or. Okay. At what temperature will sodium nitrate have this? So 95. We're looking at sodium nitrate. That's along this line. So here we go, right over there. Drop it down. It's about 30 degrees Celsius. So those are kind of pretty simple, self-explanatory. But where you guys may or may not have seen this before is a question like this. It says, what is the solubility of sodium chloride at 25 degrees Celsius in 150 centimeters cubed or milliliters of water, which is just saying 150 grams of water? Okay? Well, if we follow our same rules, sodium chloride is going to be this line right here, the one that doesn't change much. Okay? And we are at 25 degrees Celsius, so it's going to be right about there. What's that value? It's about what?
48.
No, about 38. Okay, is that our answer though? Why not?
Per 100.
Right. This is per 100 grams of water. We're asked for how many? 150. So you got to set a little proportion, guys. Have you done problems like this in the past in earth science? Okay. So this is review for you guys. I want you to go through that sheet if you have not done so already. Go through and answer those questions, and then we'll come back. Okay. What type of solution do I have? Or how many additional grams of solute must be added to make it saturated? What does saturated mean again? You said saturated is equals full. Where is that going to be in terms of the lines that we see? On the line. Okay, so this is something you may want to jot down in your notes at the bottom so that you have. Maybe you already know it. If you do, that's great. If it's below the line, though, what would we call that? What type of solution would it be? Unsaturated. What does that mean? Yeah, it's not full. There's space left that you can add more. If it's above the line, it's supersaturated. Now, guys, one key piece with supersaturated. What's that? No. I'm just using space. I'm just writing some space here. That's not the answer. Right. Oh, if it's above the line, right. It's considered a supersaturated solution. Yep. Okay. So the classic example that I used to use when I was down south, we talked about sweet tea a lot. All right. When people make sweet tea, all right, what they do is they actually heat up the water to allow more sugar to get in there to make it even sweeter. So like I've heard rumors, former students of mine have told me that's how their grandma makes it or whoever, where their sweet tea will be so sweet that when it's just sitting there in your glass, you will start to see it crystallize at the bottom because there's so much sugar in it. All right. Tomorrow I'll show you guys what a supersaturated solution looks like. Like rock candy. Anybody ever make rock candy before? Right, where you heat it up first, then you let it slowly go down because you're putting more solute in that substance that can actually be held at that lower temperature. So you have to heat it up first to then let it cool back down so you have it oversaturated. Now with that sweet tea, when it's oversaturated like that or supersaturated, any jolt, any type of thing, we'll get to start to what we call crash out of solution. And that's what I'm going to show you guys tomorrow. Something actually crashing out of solution where then, it's left over. It'll start to crystallize, absolutely. Now, just because something, guys, has extra substance, so think back to that POGIL activity that we did to start that, where you guys were counting up the particles. What did you see on a saturated solution? What was left once it got full? Where did the rest of the particles go? The bottom. Is that a supersaturated solution? No, that is a saturated solution. Supersaturated, guys, is a specific condition where the temperature has been increased to allow more particles to be dissolved. Okay? You've had to increase the temperature and cool it back down so you have more particles than what could normally be allowed to dissolve. So you have extra particles dissolved. If you have it at the bottom, it's just kind of crashed out of solution. That's not a supersaturated. That's just a saturated solution. Okay? So I wanted to kind of talk about that. So with this problem, how many grams? So you could be asked, is it supersaturated, saturated, or unsaturated? So in this case, guys, it's talking about an unsaturated solution, so we're going to be below the line. It says how many additional grams of solute must be added in order to make it saturated. So here's our conditions. Okay, we have the graph of solubility for potassium nitrate is 84 grams at 50 degrees Celsius. So 50 degrees potassium nitrate, all right, right here, we can hold up to 84. All right, but let's say we had 60 grams of potassium nitrate. You could be asked, how many extra grams would we have to add to make it a saturated solution? So if it can hold 84, but we have 60, how do we figure out how many more we can add? Yeah, we just subtracted, okay? Have you guys done a problem like that in the past? Okay, so this is all review for some of you. Some of you haven't seen it or don't remember it. All right? We're going to practice these the rest of this week. Okay?